Welcome to this lecture on the foundations of data mining and science. In this course, we're going to explore the essential tools, concepts, and ethical considerations that define the field of data science. Whether you're pursuing a career in technology, business, or research, understanding how to gather, process, and interpret data is a vital skill. Data science isn't just about crunching numbers, it's about generating insights that drive decisions in every industry. Throughout this presentation, we'll walk through the evolution of data science, examine key career paths, and dive into real-world case studies like Netflix's recommendation system. By the end, you'll not only understand what data science is, but also how it's transforming the modern world. Foundations of Data Mining and Science by the Programming Professor. Let's take a quick look at the outline for today's presentation. First, we'll begin with an introduction to data science, what it is and why it matters. Then we'll move into a historical overview, exploring how the field has developed over time. After that, we'll discuss why data science has become such a hot topic and where it's being used in industry. We'll then dive into the data science lifecycle, a framework that breaks down the step-by-step process used in real-world data science projects. From there, we'll shift our focus to ethics, an essential topic when working with data that can directly impact people's lives. And finally, we'll end with a detailed case study focused on Netflix, examining how they use data science to revolutionize content recommendation. Let's get started with defining data science. So what exactly is data science? At its core, data science is an interdisciplinary field that combines elements of computer science and statistics to uncover patterns and relationships in data. The key word here is interdisciplinary. Data science pulls from multiple domains to solve complex problems. Data scientists write code to manage and visualize large datasets, build and evaluate predictive models, and make informed decisions based on their findings. This makes them both technical and analytical professionals. Think of a data scientist as someone who can not only manipulate data using programming tools like Python or R, but also interpret the results and communicate them to stakeholders. This blend of skills allows data scientists to drive strategy and innovation in fields ranging from finance to healthcare to entertainment. Data science, as we know it, didn't spring up overnight. Its roots trace back to the 1960s, when it started to emerge as a distinct discipline. In the 1970s through the 1990s, foundational tools and models were developed, laying the groundwork for modern data analysis. During the 1990s, businesses began to seriously adopt data science for practical use, especially in areas like customer behavior analysis and targeted marketing. This period marked a transition from academic research to commercial application. A fun milestone in the development of the field came with the release of Python in 1991 and R in 1993, two programming languages that are now fundamental to data science practice. This historical context helps us appreciate how data science evolved from a niche area of study into a critical business asset. Moving into the 21st century, we saw an explosion in the scope and importance of data science. In the early 2000s, organizations such as the National Science Board began formalizing the discipline, helping define its methodologies and best practices. The release of major software tools like Pandas, scikit-learn, and ggplot2 empowered data scientists to perform sophisticated analyses with greater ease. Then, during the 2010s, data science truly went mainstream. Tech giants like Google, Amazon, Netflix, and LinkedIn began using data science at scale, shaping everything from search algorithms to personalized recommendations. Around the same time, universities launched dedicated degree programs to meet the growing demand for skilled data professionals. Today, data science ranks as one of the most desirable careers in the United States, thanks to its combination of high demand, lucrative salaries, and broad applicability across sectors. As we look toward the future, it's important to recognize that data science is still a young and rapidly evolving field. While it continues to be built on foundational techniques from statistics, It increasingly incorporates cutting-edge methods from machine learning and artificial intelligence. Tools like neural networks and deep learning models are enabling breakthroughs in image recognition, language understanding, and more. Another major area of growth is natural language processing, which powers technologies like chatbots and language translation. But as the field grows in power and influence, there's also a rising emphasis on interpretability and responsible AI. It's not just about getting accurate results anymore. It's about understanding how those results were generated and ensuring that they're used ethically. This forward-looking perspective is essential as data science becomes more deeply embedded in both industry and daily life. To work effectively in data science, we need to understand datasets. These are the raw materials we work with. A dataset is essentially a structured collection of information that can be used to identify patterns and make predictions. Each dataset is composed of features and instances. Features are the individual variables or measurements, things like height, temperature, or income. Instances, on the other hand, are the actual data points, like a single customer's profile or one penguin's physical characteristics. A helpful example is a penguin dataset, where features might include bill length or body mass, and each penguin observed is an instance. Understanding the structure of datasets is crucial, because it determines how we clean, analyze, and model the data later in the process. It's this structure that allows data scientists to extract meaningful insights from what would otherwise just be a table of numbers. Now let's talk about big data. Big data refers to datasets that are so large or complex that traditional data processing tools can't handle them efficiently. We often summarize big data using three key characteristics: volume, velocity, and variety. Volume speaks to the sheer size, think of billions of rows in a database. Velocity refers to how fast new data is being generated, such as real-time data from social media or sensors. And variety captures the different forms data can take, from text and numbers to images and video. The explosion of big data has driven demand for data scientists who can handle, interpret, and make predictions from these massive, fast-moving, and diverse datasets. It also enables businesses to personalize customer experiences and make real-time decisions, offering a major competitive advantage. Let's zoom in on the first V of big data, volume. Over the past 2 decades, the amount of data generated globally has grown exponentially. Managing this enormous volume requires powerful tools and infrastructure. Technologies like Apache Spark and Hadoop have emerged to handle distributed computing tasks, allowing us to process data in parallel across many machines. Enterprises often rely on platforms like Cloudera to organize their data infrastructure. In addition, cloud solutions such as AWS, Google Cloud, and Microsoft Azure have become essential. These platforms store datasets across multiple servers, allowing for more efficient access and scalability. A key benefit of cloud computing is that only the data you need is loaded into memory, which helps save both time and cost. Understanding volume is foundational when working on projects where the data could span terabytes or more. Now let's focus on the second V, velocity. Data doesn't just sit in one place anymore, it flows constantly. Velocity refers to how quickly data is generated and needs to be processed. This could be as fast as real-time updates from a stock exchange or as routine as daily or weekly reporting. To manage this, data scientists rely on a few key strategies. First, reproducible code allows them to update analyses with minimal manual effort. Automation ensures that scripts can be scheduled to run regularly, even daily. Version control helps track changes in code and data, which is essential for collaboration and consistency. For example, code-based models can easily adapt to new data, while more static tools like Excel are harder to update in a reliable, repeatable way. Mastering velocity ensures that insights remain timely and actionable. The third and final V of big data is variety. In today's world, data comes in many formats, not just neat spreadsheets. Structured data refers to organized tables and databases, where everything fits nicely into rows and columns. But increasingly, we work with unstructured data, like text from social media posts, images, audio recordings, and even video. This introduces unique challenges and opportunities. Data scientists must use a mix of statistical methods, computer science techniques, and machine learning models to make sense of all this varied information. For instance, analyzing a video clip may require tools for image recognition and audio processing, while a text dataset might involve natural language processing. What sets data science apart from many other fields is this ability to integrate and analyze data across multiple formats and modalities. Mastering variety is essential for tackling complex, real-world problems that don't come prepackaged in clean tables. So why is data science in such high demand? Simply put, it's one of the fastest-growing professions in the United States and globally. According to the Bureau of Labor Statistics, data science roles are projected to grow over 35% by the year 2032, a rate much higher than most other careers. But it's not just the growth rate that makes data science appealing. It's also the diversity of industries that rely on it. From computing and finance to education, government, and healthcare, nearly every field benefits from data science. Organizations depend on data professionals to make informed decisions, forecast trends, and boost operational efficiency. Whether it's predicting customer behavior, managing risk, or optimizing supply chains, data scientists are at the heart of strategic decision-making. This growing reliance on data-driven insights ensures that demand for skilled professionals in this space will only continue to rise. When we talk about careers in data science, it's important to realize that data scientist is just one of many roles in this ecosystem. Let's start with the data engineer. They build and maintain the systems that collect and process data. Their focus is on pipelines and architecture, essentially laying the foundation for data science to happen. Next, we have data scientists themselves, who develop models and extract insights. Data analysts typically work more closely with stakeholders, summarizing results and creating visualizations to support decision-making. Business intelligence analysts are similar to data analysts, but often focus more narrowly on market and financial data to drive business strategy. Finally, machine learning engineers specialize in developing and deploying algorithms that adapt and improve over time. Each of these roles plays a critical part in the data science process, and your personal strengths and interests can help determine which path is right for you. To make sense of all these roles and responsibilities, we use the data science lifecycle, a 5-step framework that outlines the end-to-end process for completing a data-driven project. While data scientists may be involved in every step, many choose to specialize in specific areas like modeling or visualization. Step 1 is gathering data, which involves identifying and collecting relevant data sources. Step 2 is cleaning data, where we reformat the data, create new features, and handle missing values. Step 3 is exploring data through summary statistics and visualizations. Step 4 involves modeling data, using algorithms to make predictions or identify relationships. And finally, Step 5 is interpreting data, which includes communicating results clearly to both technical and non-technical audiences. This life cycle is not always linear. Steps are often revisited as new questions arise. Mastering this framework is crucial to becoming a competent and flexible data professional. The first step in the data science life cycle is gathering data. This phase is all about asking, what data is available and what data do we need to answer the question at hand? Data can come in two forms, structured and unstructured. Structured data is neatly organized, think spreadsheets or SQL databases, where variables are aligned in rows and columns. Unstructured data is more complex. It might include emails, social media posts, images, or audio clips, things that don't fit into a simple table without some pre-processing. Often, data science projects use both types of data. For example, a project might pull structured sales data from a database and combine it with customer reviews scraped from the web. Understanding the source, format, and limitations of your data is foundational, because all future steps depend on the quality and relevance of what you gather at the start. Once you've gathered your data, the next step is cleaning it. This is often one of the most time-consuming, but absolutely critical parts of the data science process. Clean data ensures that your analysis and models are reliable and accurate. The cleaning process starts by combining data from multiple sources, especially when working with information collected across systems. Next, we reformat the data into a tabular structure, with features as columns and instances as rows. It's also common to encounter missing values, often labeled as not a number, which need to be addressed through methods like imputation or deletion. Additionally, we may create new features by transforming existing data, for example, converting text categories into numerical codes. All of these steps are essential for preparing the data for modeling. As the saying goes, garbage in, garbage out. Without clean data, even the most sophisticated models won't produce meaningful results. With clean data in hand, the third step in the data science lifecycle is exploring the data, also known as exploratory data analysis or EDA. This is where data scientists get to know the data, identify patterns, and uncover insights that inform their modeling choices. EDA involves both visual and statistical techniques. Visualizations like scatter plots, box plots, and histograms help highlight relationships, trends, and distributions. Summary statistics, such as mean, median, and variance, provide numerical descriptions of features in the dataset. One key goal of this step is to spot anomalies or outliers, which may skew results or signal data quality issues. Another is to begin forming hypotheses about what relationships exist in the data. This phase is a bit like detective work. You're not testing models yet, but you're asking smart questions and looking for clues that will guide your next move. Step 4 is modeling the data, where we start applying mathematical and machine learning techniques to make predictions or uncover patterns. The model you choose depends on the nature of your data and your specific goals. In supervised learning, we train the model on labeled data, where the outcomes are already known. This includes classification problems, where we predict categories like fraud or no fraud, and regression problems, where we predict continuous values like housing prices. On the other hand, unsupervised learning involves data without predefined labels. These models look for hidden structures in the data, such as clusters or associations. Examples include customer segmentation or topic modeling. Choosing the right model, tuning its parameters, and evaluating its performance are all key steps in this phase. Modeling is where we transition from understanding the data to making it work for us. Once a model has been built and tested, the next step is interpreting the data. This involves clearly and accurately communicating your results to others. A strong interpretation phase bridges the gap between complex technical work and actionable insight. When speaking to technical audiences, such as other data scientists or engineers, you might focus on the details of the model, the training process, and evaluation metrics like accuracy or RMSE. For non-technical stakeholders like business leaders or clients, the emphasis shifts to key findings, data visualizations, and concrete recommendations. Your job is to translate numbers into narratives. Interpreting the data can also reveal areas for improvement, such as a need for more data collection or model refinement. In many cases, your insights will directly influence decisions in policy, product development, or research. This is where the work becomes impactful. Now that we've covered the core life cycle, let's take a moment to talk about ethics in data science. Ethics is not just an optional add-on, it's central to the responsible use of data. Every decision a data scientist makes can have real-world consequences. For instance, in areas like healthcare or finance, a poorly designed model can lead to unfair or even harmful outcomes. Ethical data science begins with how we handle the data itself. It must be kept private and confidential, especially when it involves sensitive personal information. Data must also be checked for bias, as skewed or unrepresentative datasets can reinforce existing inequalities. Some industries are tightly regulated, but many types of personal data still fall outside legal protection. That means it's up to us as data professionals to proactively ensure that our practices are fair, transparent, and respectful of individual rights. One of the most important aspects of data ethics is protecting privacy and confidentiality. Datasets often include sensitive personal information, things like names, addresses, income levels, or even health records. It's the responsibility of data scientists to implement safeguards to protect this data. That includes secure storage, limiting access to authorized personnel, and anonymization techniques. Anonymization can involve replacing personal identifiers with ID numbers, grouping data into categories, such as using age brackets instead of exact ages, or slightly modifying numerical values to obscure individual identities while preserving overall patterns. The goal is to maintain the utility of the data without compromising privacy. These practices are especially vital when publishing datasets or sharing them across teams. Failure to handle private data responsibly can lead to ethical breaches, legal issues, and loss of public trust. Data privacy isn't just a technical concern, it's a fundamental part of ethical decision-making in our field. Another key ethical concern is algorithmic bias. Bias in data science occurs when models produce unfair or discriminatory outcomes. This isn't just a theoretical issue, it can have real-world consequences in hiring, lending, policing, and healthcare. Bias often stems from underrepresentation in the training data. For instance, if a facial recognition system is trained mostly on lighter-skinned individuals, it may perform poorly on darker-skinned faces. Historical bias is another factor. Models trained on biased past decisions can replicate or even amplify those inequities. The result is a feedback loop that reinforces systemic discrimination. Data scientists need to actively test for and mitigate bias during model development. That includes auditing datasets, analyzing model outputs across demographic groups, and considering fairness metrics alongside accuracy. Algorithmic bias isn't always obvious, which is why ethical awareness and inclusive design are essential components of responsible data science. Data ethics extends beyond privacy and bias to include how personal data is used to influence behavior. One of the most notorious examples is the Cambridge Analytica scandal. This political consulting firm acquired data from 87 million Facebook users, largely without their consent, and used it to build psychological profiles. These profiles were then used to target political ads, aiming to influence opinions and voting behavior. The scandal raised serious questions about consent, transparency, and manipulation. Who owns your data? How should it be used? And what rights do individuals have when it comes to their digital footprint? These are ethical dilemmas data scientists must grapple with, especially when working with behavioral or social media data. The Cambridge Analytica case is a wake-up call about the power of data and the responsibility that comes with it. It reminds us that data science doesn't exist in a vacuum. It interacts with society, politics, and human rights. Data science also has environmental implications, both positive and negative. On the positive side, data science helps us better understand and model climate change. It supports the development of tools to optimize energy usage, reduce waste, and plan more sustainable cities. However, the field isn't without its downsides. Large-scale data centers where data is stored and processed consume massive amounts of electricity. In the United States alone, data centers use about 2% of the nation's electricity, while globally the number is around 1%. Moreover, computationally intensive tools like neural networks and complex decision trees require significant energy, especially when run at scale. As data scientists, we should be mindful of the environmental cost of our models and consider ways to reduce energy consumption. This might mean choosing simpler models when possible or being efficient in how and when we process large datasets. Sustainability should be part of our ethical toolkit too. Let's now shift into a real-world case study, Netflix and its algorithm Cinematch. Netflix launched back in 1997 as a DVD rental service, and in 2000 it adopted a monthly subscription model that changed how people accessed entertainment. A key innovation behind the scenes was Cinematch, an algorithm that predicted what movies a user might enjoy based on previous 5-star ratings. This early recommender system helped Netflix offer personalized recommendations, which in turn kept users engaged and reduced churn. It was one of the first large-scale examples of data science being used in a consumer-facing product to drive business success. The algorithm didn't just recommend popular titles, it learned from each user's preferences to deliver tailored suggestions. This use of predictive modeling based on user behavior laid the groundwork for many of the recommendation systems we now take for granted in services like Spotify, Amazon, and YouTube. In 2006, Netflix took its commitment to improving recommendations to the next level by launching the Netflix Prize. This competition offered a $1 million reward to any team that could improve the accuracy of its Cinematch algorithm by at least 10%. The challenge sparked global interest, drawing participation from academic researchers, professional data scientists, and even hobbyists. Netflix released a massive dataset to competitors, nearly 18,000 movies, close to 500,000 users, and millions of individual ratings, all anonymized but time-stamped. The evaluation metric was RMSE, root mean square error, a common way to measure the accuracy of predictions. The idea was simple: improve predictions of how users would rate movies, but the execution was anything but easy. The competition demonstrated the power of crowdsourcing and open innovation in data science, and it quickly became one of the most famous machine learning challenges of the decade. As participants explored the Netflix dataset, they faced a range of real-world challenges that made the problem more complex than it appeared on paper. One major issue was the uneven number of ratings. Some users rated thousands of movies, while others rated only a few. Similarly, certain movies had thousands of reviews, while others had almost none. This imbalance made modeling more difficult. Another complication was the lack of metadata. There were no genres, actors, or plot descriptions included in the dataset, which meant teams had to rely entirely on the rating patterns themselves. Despite these limitations, the competition progressed steadily. In 2009, a team named Belcor's Pragmatic Chaos finally achieved the required 10% improvement. Interestingly, another team, the Ensemble, also reached the target, but submitted their result just 20 minutes past the deadline. As a result, Belcor was officially declared the winner. These kinds of high-stakes, close-call outcomes are common in competitive data science. The winning algorithm was evaluated using RMSE, which penalizes large errors more heavily than small ones, making it a rigorous metric for assessing predictive accuracy. Belcor's final model was incredibly accurate, combining dozens of algorithms in an ensemble approach. But there was a catch: it was also highly complex. The model had great predictive performance on the competition dataset, but it wasn't practical for Netflix's actual production system, which needed to scale to over 5 billion ratings. In the end, Netflix opted not to use the exact winning algorithm. Instead, they developed a simpler model that was faster and more efficient, while still delivering significant improvements in recommendation quality. This decision highlights a critical point in data science: accuracy isn't the only metric that matters. Real-world systems need to balance performance with scalability, speed, and maintainability. Sometimes, a slightly less accurate model that runs efficiently is the smarter choice. Even though Netflix didn't implement the winning algorithm, the impact of the Netflix Prize was enormous. It fundamentally changed how companies thought about recommender systems and user personalization. The competition introduced new modeling techniques and ensemble strategies that would later be applied across e-commerce, entertainment, and digital marketing. It also sparked public debate around data privacy. In 2009, a lawsuit alleged that even though the data had been anonymized, researchers were able to de-anonymize some users, specifically LGBTQ individuals, by cross-referencing the dataset with public movie ratings. This raised ethical concerns about whether truly anonymous data is ever possible. As a result, Netflix canceled a planned follow-up competition. The legacy of the Netflix Prize is a blend of technical innovation and ethical caution, reminding us that progress in data science must always be paired with responsibility. To wrap up, let's summarize the key takeaways from this presentation. Data science is a dynamic and interdisciplinary field that draws from statistics, computer science, and domain expertise to generate insights from data. Understanding big data through its volume, velocity, and variety is crucial to working effectively in modern analytics. We explored the five-step data science lifecycle, from gathering and cleaning data to modeling and interpreting results. Careers in the field are diverse, ranging from data engineers to machine learning engineers, each playing a vital role. But technical skill alone isn't enough. Ethical considerations, especially around privacy, bias, and environmental impact, are central to responsible data science. Finally, the Netflix Prize case study illustrated the power and complexity of real-world data projects, highlighting both the potential of data science and the challenges it presents. As you move forward, keep these lessons in mind. Be curious, be critical, and be ethical.
Thanks for watching. Let me know in the comments if there are other topics you would like me to talk about. If you enjoyed this video, please like, share, and subscribe for more content on software engineering and technology. See you next time.